All right, Calculus 2 students, we're going to move on to another graph now. In MyOpen Math, if we click on the second of these circles, cardioids and limaçons, and I'm okay if you don't remember all the terminology here, but the limaçons are the ones that had the loop in them, whereas the cardioids are the ones that are a little more heart-shaped, and of course you know what circles are. But let's click on the next group of these. And these are exactly the same as the ones we saw before, except I've replaced the cosine theta with a sine theta. So let's start by hitting play. And we see the exact same type of shape, except it seems to be oriented a little differently than the ones we saw in the last video. If we think of the last ones as being oriented horizontally, then these are now oriented a little more vertically. And that has to do with the complementary relationship between sine and cosine. The co in cosine actually can be thought of as complementary, dealing with complementary angles. And those are angles that are related by 90 degrees. So if you've got a sine of an angle, then cosine of 90 minus that angle will be identical. And so that's going to explain the rotation, and you can play with this and experiment to see the same type of behavior that we saw in the previous video. Now, where do the circles come from? So let's stop this for a moment and let's just sketch the whole graph. So a circle is going to be a graph that has a center, and then every other point is going to, or every point on the curve is going to be the same distance from that center. We're going to focus here on circles that are centered at the origin. And if you think about this r theta relationship, if the distance from the origin was independent of the value of theta, if it was always the same, then that would be like we left the theta out completely. And yes, indeed, if I consider r equal to a, all by its lonesome self, that means every angle that I plug in is going to give me the same value of r. And that's going to give me a circle. And so let's actually shrink b down to 0, and there we get our circle. And if we increase a, we're increasing the radius of the circle, and if we decrease a, we're decreasing the radius of the circle. Now when a is negative, okay, now we have r equal to a negative value. It's going to go in the opposite direction, whatever distance is otherwise indicated. And so you can see as we go further negative, we're increasing the radius as well, but the drawing of that is actually done in a slightly different manner. With positive values, when we draw, we start over on the right. Maybe I can shrink that down, make it a little bit easier to see. But with negative values, we start over on the left and proceed still in that counterclockwise manner. Okay, so once again, the circle is obtained with r equal to a constant, and so constant functions are no longer the horizontal lines that we remember from Cartesian coordinates or rectangular coordinates. The constant functions, r equal to a constant, are going to give us, in fact, the circles. And if you think about the difference between rectangular coordinates and polar coordinates, rectangular coordinates are built on lines, either vertical or horizontal. And so it makes sense that if you have x equal to a constant or y equal to a constant, then you're going to get horizontal and vertical lines. The polar coordinates, on the other hand, are built on direction angles and circles. So it makes sense that when r is equal to a constant, you're going to get a circle. And you might want to think about what happens when you have an equation theta equals to a constant. That one is actually something that Desmos is not yet capable of doing. At least I've not found it to be the case. But if we think about it for a moment, if we know that theta is equal to pi over 3, and the r can be anything it likes, that means we can head in that direction any amount we like, and even go backwards in the opposite direction. And so in fact, an equation of the form theta equals a constant is going to give you a line through the origin that is going to be related to that particular theta value for the angle. Okay, well otherwise this is going to be the same as what we saw previously. So let's actually leave this for now and move on to some other graphs. So down here we have roses. I think I'll just do one of those now that you've learned the difference between the cosine and the sine effect on the graph. So let's just pick the sine one here. And once again, we can toggle all of these values, the a, k, and phi. So I'm just going to hit play. And these are called roses because they're floral in nature and have petals. What is happening in this particular case with k equal to 2 is that we have 1 times sine 2 theta. That means we're not computing the sine of theta, but sine of twice the angle. Let's see what happens when we do that. First, when I plug in a 0 for theta, I'm going to have sine of 0, which is 0, and so my r value is 0. And as I see this drawn, you can see it started at the origin where the radius is 0, and so that makes quite a bit of sense. But what happens beyond that? Why does it seem to go out to a certain place and turn around? Its maximum value seems to be achieved at pi over 4. And when you increase your angle beyond pi over 4, all of a sudden the radius starts to decrease and it gets back to 0. So let's plug in pi over 4 and see what that does for us. When I plug in a pi over 4, I'm going to then double that value. In this case, I'm doubling because k is equal to 2. We're going to change k in a moment and see what else happens. But if I'm doubling pi over 4, what I actually get inside my parentheses is pi over 2. And sine of pi over 2 is 1, and that is the maximum value of sine. So we can see that at pi over 4, since we double the angle, we're actually achieving sine's maximum value. On the other hand, when I plug in a pi over 2, where I'm used to seeing sine achieve its maximum value, I have to double that. I have to multiply by my k value. And twice pi over 2 is pi, and sine of pi is 0, and that explains why this is shrinking back to 0 at that place. As we cycle through more angles, we get negative values and some more positive values. And so as before, I would encourage you guys to plug in some theta values a little by little. And you're going to find out that once again, this is going to complete its drawing at 2 pi. But let's see what happens then whenever I look at k equal to 3. So now I'm tripling the values. And so I have to look at triple the angle. And if I triple pi over 6, I get pi over 2. This is shifted where that maximum occurs. And notice for this odd value of k, 3, I've gotten back to the origin now halfway through at pi. And beyond that, I seem to be retracing the curve. You don't see anything new appear. And you can verify that by plugging in values. So there's a difference between the even and the odd values of k on these graphs, because sometimes they retrace values, and if I increase the 4, sometimes they duplicate. And so you can experiment with different values, and you can see that with the even values of k, you're going to have a number of petals equal to twice the number of k. But with the odd, the number of petals is precisely the number of k. Now a is going to just increase the size. Okay, and of course the negative will have an effect as well. And so once again, this is something for you to play with. And so we can hit play. And as the value of k increases, the period is going to decrease. And so from 0 to 2 pi, we actually have a lot greater repetition of the graph. And it's very, very quick to draw. So if I have k equal to, let's say, 10, I don't have to scroll very far before I see a significant amount of the graph. Okay, for the even numbers, it'll take all the way to 2 pi to complete the drawing. And for the odd numbers, at pi over 2, it'll be complete and then start to repeat. Okay, well, this video is now, I believe, at about 10 minutes, a little over, so I think I'll stop it and start another video.